Hello and welcome to today's session. This is Blanka Horvath. I am replacing Paul B. Lokon. So there is the little conundrum in the beginning of the slides is solved with that. So normally Paul would give the session, but I'm replacing him for today. If you have any questions, please on the chat. Very well. I will be notified by Ed here in the room. So let's start. So what we will start with is one of the building blocks of principal value decomposition. So principal value decomposition is one of the main ingredients or one of the main ways to dimensionality reduction. And here we will review something very basic and simple from linear algebra, and we will go through this thoroughly so that we make sure what are these components that lead to principal component analysis. Basically, the idea is going to be in a high dimensional space, there are many components, many vectors that contribute to some kind of observation, and we want to find those axes or those areas that are the few most important ones so that we can feel free to leave away the ones that are less important. And for this we have to find the right coordinate system in our high dimensional vector space, and this is exactly what we are going to do. We will go through the vectors and the vector analysis now in detail. All right, so what do we need for this? Little linear algebra review. I'm looking here in the room. I'm guessing that this is probably something that you have seen, but still bear with me. We go through it anyway in detail. It never hurts. Good. So square matrix is clear to everybody. Where do I? This is the little dot. That's wonderful. Okay. So you see, this is the square matrix. So what do we do? We take some kind of transformation, this transformation matrix A, which we apply to a vector. For now, we don't really say anything about the meaning of these vectors and the transformations. Usually when we multiply the vector with the matrix, what happens is that this matrix changes direction, meaning if it was 2 and 3, this is a different direction, as we will see in the next slide in the picture. But there are a few cases when the direction is preserved. So what would that mean? We have some matrix, we took now the exact same matrix, we take a different vector, so we find a direction such that the result vector is a multiple of the first and of the second entries. We could also write it for another vector, 1 and 1. If we multiply this through, then we get -2. Let's just do it with one of them, because why not? So 2 times 1 minus 4 times 1 is -2, and the second one is 1 times -1 plus -1 times -1 is again -2, which is a multiple of 1. So we can rewrite the whole thing one more time as the original vector times 3, and in this case as the original vector times -2. So that means that we have guessed or found 2 eigenvectors, -4 and 1, and the other one is 1 and 1. Are 2 eigenvectors for this transformation that we denoted by A in the beginning. So far so good. This is what it looks like in formulas, and this is what it means in pictures. So many times if you again see this transformation A, to this, if you apply to -4 and 1 to this vector, it just gets multiplied by 3 from here to here. And the other one, 1 and 1, if you apply the transformation A, it gets multiplied by -2, which you get over here. So by this transformation, nothing really happens in the direction of these vectors. It just gets longer or shorter. I might want to go up back again. I'm not sure if this is visible. Please give me a sign, people in the other end of the room, if you see it or not. So we do say that the direction is preserved even though it is reverse. So if you once go up, let's go back down. So in this case, the direction is actually reversed. We did not make the vector longer, but we went into the opposite direction, -2, but we still say that it is within the same line, so we still say that it is an eigenvector. Now just let's go back to this number over here, 2 and 3. What would happen with this one? So number 2 and 3 would be over here. This would change completely to, let's go back to the first one, to -8 and 5, to -8 and 5, to something there. So this would be a vector that completely changes direction from somewhere here to somewhere there, and this is the typical case. And for the eigenvectors, it is something special that they actually remain on the same line or reverse the direction. So these eigenvectors are somehow a special thing, a very interesting thing for us to find, and now we're going to go into understanding how to find these eigenvalues. By the way, this word eigen, it comes from German, and it means self. So it kind of reflects the idea that it is mapped by the transformation onto itself, or onto the same subspace. So let's go further and formalize this idea. We say that since for any matrix, A times 0 is equal to lambda times 0 holds, without any surprises, we should exclude the 0 vector when we speak about eigenvectors. But except for the 0 vector, we say that V is an eigenvector of this transformation A, and lambda is the corresponding eigenvalue if this relationship holds. A times alpha V is equal to alpha times AV, which is so far not surprising. This is just a scalar multiplication. The important and interesting part comes in here, that this is alpha times lambda V. So this AV is equal to lambda times V. This is where the property eigen comes in. The alpha, for now, is a bit surprising. It even got me confused. But this emphasizes basically that if V is an eigenvector, then any scalar multiple of V is also an eigenvector. Right, so if we finally found one dimension which remains invariant within or for this transformation, then of course multiplying a vector by something alpha is not going to change anything about this dimension, right? So this is basically the dimension that we're interested in, the entire line, alpha going from -infinity to 0 and from 0 to +infinity, to the same eigenvalue. So this is the eigenspace. Okay, so we can just go ahead and pick alpha being equal to 1 over the norm, so the length of the vector, which is nice because in this case we can say that we have a unit eigenvector, and then whenever we multiply it with the matrix A, then we get a vector that corresponds to the actual value, the eigenvalue corresponding to that eigenvector. Okay, so we do this, we normalize the idea, and we say that we choose always from the list of possible vectors V, the unit eigenvectors. So the ones that have unit length. Why not?